Okay, let's do the Towers of Hanoi. So Towers of Hanoi are a problem where you have three towers and you want to move all the tiles. Let's see, do Towers of Hanoi. You have these, here it is. You have these disks and they're from largest to smallest piled up on one peg or post and they form a tower. And you want to move them all. There's three of these posts. This picture only shows two. There's a third one. And you want to move them all from tower 0, which is where they start, to tower 1, which is this tower. You can also move them to tower 2. And there's only two rules. The first rule is you have to move one disk at a time. And the second rule is you can never put a larger disk on top of a smaller disk. So we to move say two disks here. Let's go here and let's see if we see something going on here. Here. So here is an iterative algorithm for solving the 6-disk problem, and you can see it's pretty complicated what's going on. It's inobvious when you look at it what the next step is going to be. But in the end, every time there's a move is always placing a disk onto either an empty post or onto a smaller disk. I'm sorry, onto a larger disk. So, so let's go ahead and solve this. So the way you do this recursively is with magic. What you say is, what if I knew how to move all of the disks from one post from say post 0 to post 1, or more generally from post, let's call them X, Y, and Z, from post X to post Y. If I can move them all from post X to post Y, I'd be done, because what I would do instead of moving, if I moved all of them, I'd be done. But if I could do it recursively, remember, you have to assume you could do it for like all but one. So what I would do is I'd move all but one out of the way. I'd take them from X to Z. I'd move the 1 from X to Y. And then I'd move them all from Z to Y. And that's what this says to do right here. That's what this is saying. Of course, there's magic going on. But the beauty of recursion is you assume it works for the smaller case. And then as long as you get your base case right, this is going to actually work. So you turn this into Python, and this is what we get. That's a move, to move n disks from a post to another post. The via is that third post that we're going to use to temporarily hold on to the n-1 disks while we move the 1 disk to our destination. And then we'll move the n-1 from that temporary post to the target post. So if we want to move 2 disks from post 0 to post 1 using post 2 as the temporary, if we run this, we get Stack Overflow. Because of course we do. These are all recursive. There's no base case here. How can it possibly work? So what is our base case? Our base case is when you want to move only 1 disk, because if you want to move only 1 disk, move it. And that's what happens here. If you want to move 1 disk, we'll move it, which here, since we can't physically move it, we'll print out the from and the to. We'll print out, move the disk from this post to that post. And now when we run this, we see 0, 2, 0, 1, 2, 1. And to show you what that means, here's stuff from our old fib. If we have, say, 1, 2, let's see, this is post 0, post 1, and post 2. And we'll do B, and we'll do A. So you can't put a letter on top of a letter that comes, you can't put a letter on top of a letter that comes before it. So this is correct. This is where we start. That's 2 on post. Now, to move from 0 to 2, we're going to take the A and we're going to put on post 2, which gives us this right there. Now we're going to move 0 to 1. So we got the A out of the way, basically, so we can move the B from 0 to 1. Nice. And now that the B's are there, naturally we can move the A from 2 to 1, which is what this says to do. So you take the A out of here, and you put it in 1. And you can see this is the sequence of moves. And maybe if I put a little extra return between each, you can really see Naturally, all these moves are legal, and we move the stack or the tower from 0 to 1. So this is actually a correct solution. And we could actually do this for moving 3. We run it. We'll see we have a longer solution. I'll leave it to you to convince yourself that works. Or 4 and longer still. But definitely works. So this solution works. But it's not as elegant as we'd like because it's how you invoke this problem. The caller just wants to say, solve the Tower of Hanoi problem with 2 disks or with 3 disks. This 0, 1, 2 stuff is an implementation artifact. It's really not something that's built into the problem. So the way we do it is create another function called Hanoi that only takes n, and it moves n, but it provides the 0, 1, and 2 into move. So that to solve this problem now, you only call Hanoi of 4 or Hanoi of 3 and so forth. And when we run this, sure enough, Hanoi of 4 prints out that nice solution. And you could, if you'd rather print it, we could actually return a solution from Hanoi as well. But here we're just printing. And here we add the trick from above with the depth and with printing out the depth. And now when you do that, you can see that Hanoi to solve a Hanoi of 4, you have to move 4. Let's see, so we want to solve Hanoi of 4. So that we want to we're trying to move 4 from 0 to 1. To do that, you have to move 3 of them out of the way. Then you have to move 1, and finally move the 3 that you moved out of the way over to the target. Now, a sub-problem of moving 3 from 0 to 2. To do that, you got to move 2 out of the way, which means 0 to 1. What's really interesting here is the target of the first move became the temporary of the second move, became the target of the third level. So as you recurse, the thing that is the source and the target and the via all move around. They change as you go. In any case, you can run this and you can look through this entirely and make sure you believe and understand everything that's going on here. Nice. All right. And now this version is iterative. So this version is insane. Look at this code right here. This code solves the towers of Hanoi. There's no recursion. This iterative Hanoi is not calling itself. It has this function f, which is a little complicated, and then it's returning f and just some stuff going on that you don't really need to know about with this vertical bar that you don't need to know about because we don't do bitwise stuff, and this is using stuff that you don't need to know. But it works. And then recursive Hanoi, of course, is the one we just wrote, and this compares the two of them to show that they're equal. And when we run this, we find out that they are equal. So the reason this is interesting, if it's interesting, is as such. Some problems have a pretty clear recursive solution and a pretty clear iterative solution. Think GCD. Some other problems have a very clear recursive solution, like Hanoi, and even though they have an iterative solution, that's clear as mud. And if I was going to implement Hanoi, I would definitely want to implement it recursively, because I believe there's a clarity and a beauty to this solution that is lacking in this solution. This one has a certain almost mystic quality that it works, but it doesn't have clarity. And I think most people would struggle looking at it to convince themselves that it actually works. Whereas this one, I think, once you get your head wrapped around how recursion works, it's actually pretty easy to convince yourself that this works. And more to the point, you can actually prove that it works using mathematical tools that, at least at CMU, would be taught in a course like Concepts. So that brings to a close our conversation of Towers of Hanoi.